Okay, many thanks, Yua, for the introduction, and very happy to be in this very distinguished workshop. What I'm going to talk about are some recent regularity results on mu-elliptic non-autonomous problems. So, to keep things simple, what am I talking about? For simplicity, let's look at variational integrals that are autonomous, meaning that they depend only on the gradient variable. L is smooth, C2, whatever you want. So what is mu-ellipticity? Mu-ellipticity is a degenerate form of ellipticity, which is formulated in this form. Here you can see the lowest eigenvalue of the Hessian of L, and the highest eigenvalue of the Hessian of L. And mu is a quantity larger or equal than 1. Now, what is the peculiarity of this formulation? Well, first of all, it is intrinsically non-uniformly elliptic, in the sense that just as by formulation, without imposing nothing, what you see is that the ellipticity ratio, which is precisely the ratio between the highest eigenvalue of the Hessian of L over the lowest eigenvalue of the Hessian of L, blows up, okay, as a positive power of the gradient variable, or in any case, as an increasing function of the gradient variable. Indeed, this G here is in general a non-negative function that will have at most power growth. Okay, it will take precise value depending on which model we are looking at. Now, in general, the variational setting is the most appropriate one to handling non-uniformly elliptic problems. Now, let's say that mu-ellipticity has another form of pathological behavior that emerges. Indeed, as for instance observed by Jacquint and Just in their Crelle papers, but you can find as many references, earlier references you want in the literature, what is crucial when dealing with the non-uniform ellipticity is to find uniform bounds on the gradient level. Okay? Once you have found them, then you can trace the equation back, in some sense, to the uniformly elliptic setting, and then, in case your operator allows, you can boost regularity up to, say, infinity, whatever. However, what happens for mu-ellipticity? For mu-ellipticity, what happens is that if we look back at the formulation, you see that the lowest eigenvalue of the Hessian, which is the one that quantifies the amount of ellipticity of your problems, becomes smaller and smaller the larger the gradient variable becomes. This means that this nice guy is playing against your attempt of proving gradient boundedness. Okay? And this is pretty difficult to handle. Okay? While, for instance, if you think to the P Laplacian, the degenerate one, P larger than 2, the eigenvalue there behaves as modulus of z to P minus 2. Okay? Therefore, the ellipticity of your problem enlarges whenever z becomes larger. So this, in some sense, helps you to prove gradient boundedness. Okay? This is not the case for mu-ellipticity. And therefore, the key crucial point is achieving gradient boundedness. Okay? And it is not easy. Okay, now, mu-elliptic models. Well, first of all, the most celebrated one, the area integral. Mu here is equal 3, G is just 1, okay? And this can be, of course, generalized up to some extent. Okay, those are, of course, fundamental model in geometric analysis. But there are also models that find important applications, for instance, in nonlinear elasticity or in material science. For instance, logarithmic energies. Here you can see just the L log L1, where mu is equal 1 and G is the logarithm of 1 plus modulus of Z. Or you can, in principle, also iterate this logarithmic by generating this form of energy, where mu is any number essentially larger than 1, and G is the iterate before, the previous iteration, than the one that defines your energy. For instance, this find applications in in the modeling of Prandtl-Ehring fluids. So let's say that it's not just fantasy, but those models appear somewhere. Okay, now what do we know about regularity? Again, autonomous integrand. Let's say that mu stays between 1 and 3. This is when we can say something about regularity, and I think it's pretty classical. And it dates back essentially to the fundamental work of Bombieri, De Giorgi, and Miranda, who treated the case of non-parametric area of the non-parametric area integral in the scalar setting, which was streamlined later on via sort of nonlinear potential theoretic approach by Trödinger, and generalized the extent to quite a large class of non-uniformly elliptic equations by Ladygensky and Duraltseva and Leon-Simon. Okay? Now, what is funny here is that if mu is larger than 3, then nothing is known about regularity. We do not know if minimizers are regular or are irregular. Somebody might bet on the irregularity, but who knows? Okay, nothing about this is known. There are, since then, huge literature flourished, very, very fine papers concerning full regularity of minima, as well as partial regularity. Okay? So, what extra, can we, in a sense, include also a little bit of anisotropy in all of this? Well, this is the case of so-called anisotropic mu ellipticity, which is defined in this form, or if you like, mu q elliptic integrals, okay? They just include an extra growth from above for the Hessian of L that might incorporate some faster growth, okay, indeed for the Hessian, for the gradient variable. Okay, first regularity result in this respect is due to Fuchs and Mingione. They proved that whenever Q, so the upper power growth, the growth of the Hessian, and the ellipticity quantifier are satisfies a certain form of constraint, okay, of this form, then one can prove that minimizers have locally elder continuous gradient. And this result can be extended, of course, to the vectorial setting, provided that your integral, of course, satisfies Uhlenbeck structure. They can also cover the iterated logarithmic stuff, and moreover, they can cover, in the scalar setting, of course, also obstacle problems. Okay? Partial regularity has been treated later on by Bildauer and Fuchs. But the thing is, what happens if I want to make my non-uniformity range, meaning the range among which I'm allowed to let Q variate in order to guarantee regularity, can be maximized or made non-dimensional, if some a priori assumptions are taken. For instance, if I assume a priori that minimizers are bounded, okay, I can prove that, Bildauer and Fuchs, you can find this theorem in the book of Bildauer, can prove that the gradient is locally elder continuous. Now, how do you prove this? Well, you prove it by using a sort of unbalanced iteration, Moser iteration alla Marcellini, okay? Combined, in order to account for the a priori and infinite information, combined with a Gagliardo-Nirenberg type inequality. Beautiful? What is some sort of drawback of all this technique? Well, you need the availability of second variations, meaning that you want to differentiate twice your integral. So just keep in mind this, and let's see what's going on. We saw that the range, the non-uniformity range, must be in some sense restrict. Okay. In particular, not all possible values of mu and q are admissible. Yes. And what if we would like to make a comparison with the superlinear literature, because in general, as we have seen, mu ellipticity is typical of problems at early, either linear growth, the area case essentially, or nearly linear growth, the logarithmic one. So if just formally you allow me to take mu less than 1 and formally pose p equal to 2 minus mu, then mu q ellipticity becomes the more classical PQ non-uniformity, right? Which is formulated exactly in this form. You are essentially trapping your echelons between two identities times two different powers of the gradient variable. And this is in some sense a smart way to handle non-uniformity, in the sense that you are quantifying the grow ellipticity features of your echelon to the rate, and you are linking them to the rate of blow up of the ellipticity ratio. I mean, this can give something. Indeed, the basic principle behind non-uniformity is that you have hopes of proving regularity whenever the ellipticity ratio doesn't blow up too fast. Okay? You need to impose some sort of a threshold on it in order to contain it. Otherwise counterexamples may emerge. And this was classical work of Marcellini and Giaquinta. In particular, let me highlight that as a precise parallel with the mu elliptic situation, also in the PQ1, nothing is known about the optimal threshold for autonomous problems. Okay? The only thing that is known is the bound concerning the optimal threshold that guarantees boundedness of minimizers, right? The counterexample was constructed by Marcellini in the most general form in 1991, while the positive result is a very nice achievement of Hirsch and Schaffner 30 years later. Yeah, so at the gradient level, in the autonomous setting, nothing is known. Okay? Okay, so this suggests that already for autonomous problems, we are not free to choose to take an arbitrarily large range of non-uniformity. Okay? Otherwise, counterexamples appear, minimizer may not be even bounded, and whatever. So the idea is, what happens if I plug in coefficients? But, well, the situation can only get worse, right? Yes, it gets worse, but it gets more clear. And this is a common feature of this class of is a common feature of non-uniformly elliptic problems. Let me show why. Well, let's look, for instance, at the double phase energy. It doesn't need presentations. I mean, this was introduced by Zhikov in the setting of homogenization and for proving possible occurrence of Lavrentiev phenomenon. As you can see, the double phase is perfectly pointwise uniformly elliptic. What is the problem? Well, the problem is that the coefficient doesn't have enough positivity to rebalance oscillations around the point. Therefore, what happens? It happens that the double phase energy cannot be trapped between the same power of the gradient variable. And this gives rise to a very, very mild form of non-uniformity, okay, that cannot be spotted by the classical ellipticity ratio, but a slightly modified version of it, that is the non-local ellipticity ratio, that measures somehow the contribution of the coefficient to the non-uniformity of the problem. It's something that also appears in homogenization, right? Something like the ellipticity contrast that tell you at each fixed scale how the ellipticity of the operator goes. Okay? So it's something pretty ubiquitous, if you like. However, why this is interesting? Because the guy is a provider of counterexamples. For instance, this is due to Fonseca, Mali, and Mingione that built on a construction of Zhikov. And what's happening here? Well, what is happening is that whenever you violate a certain threshold, then you can construct a family of double phase problems with smooth boundary datum, defined on a both, so smooth domains and whatever, such that the set of essential discontinuities has almost maximal Hausdorff dimension. Concretely speaking, what happens here is that your minimizer is not better than W1, P plus sigma, okay? So in particular, you are not going to W1Q, in particular, you are not going to W1 infinity. That's it. So minimizer can be pretty bad. And it can be said even more. Indeed, this result has been later on streamlined by Balchi, Dinning, and Surnachov. What they proved for bounded minimizer, that you can actually be as bad as any W1P map. Actually, you cannot be any better than W1P whenever you violate, for instance, a threshold of this form. Okay, what happens? Solutions to Dirichlet problems as a set of essential discontinuity of maximal Hausdorff dimension equal to n minus p, meaning that you are not going outside W1P. Moreover, Lavrentiev phenomenon occurs in Dirichlet classes defined upon smooth boundary datum, and moreover, the density of smooth maps in modular convergence simply fails. So, pretty bad things might happen. What is let's say, the moral behind this is that, again, the non-uniformity range must be restricted. Otherwise, pretty unpleasant phenomena might happen. Concerning regularity for a priori bounded minimizers under this condition, we have the result of Baroni, Colombo, and Mingione that tells you that the gradient is locally Elder continuous. It is okay. And okay, this has been, of course, extended to a very general class of pointwise uniformly elliptic structures that are indeed pointwise uniformly elliptic, but they cannot be trapped between the same power of the gradient variable, so a sort of non-standard growth. In this case, the very mild form of non-uniformity that is caused by ill-behaved coefficients essentially is rebalanced using some, if you want, a bit of Elder continuity alla De Giorgi and Ashmoser, okay? Which comes precisely because your operator is pointwise uniformly elliptic. Otherwise, there would be no chances in hell you're going to prove this, okay? Now, let's try to see, either in the case of mu-q elliptic problems or pq elliptic problems would be more or less the same. I mean, the same point of view, if you want. Let's try to see if I can follow this idea of looking at the frozen integrand. What happens? Well, I just put myself in the very basic model situation. I freeze. I look at the growth ellipticity prescriptions that I have, and I look at the ellipticity ratio, and then I simply blow up as a positive power of the gradient variable. And so any sort of perturbative approach to the regularity of this class of problems simply breaks down immediately. There are no ways in hell you're going to do this. Okay, so it is rather a classical fact that whenever you have uniformly elliptic problems with Elder coefficients, solutions are correspondingly Elder continuous. And of course, corresponding open problem, can I say the same for in the non-uniformly elliptic setting, whatever the rate of non-uniformity it is, right? Okay, now, an answer to this question that was raised at several stages in the literature by several authors was offered by myself and Mingione for the case of PQ non-uniformity, and for the case of anisotropic mu-ellipticity is again myself and Mingione, and myself, Filomena De Filippis, and Mirko Piccinini. Okay. I'm going to focus this day on those two papers, essentially. Now, what is the key of our approach? Well, since the 30s of the previous century, the only way you have to prove gradient boundedness in non-autonomous, of course, uniformly elliptic problems was to first prove Elder continuity up to some exponent. Then to step back, retain just gradient boundedness, and then push the Elder continuity as much as your operator allows. This was more or less the point of view adopted since 1930. What we do now is instead a different thing, a direct proof of gradient boundedness, okay? Now it is the solution or a suitable approximation of the solution that iterates and produces regularity. All previous approaches, what did they do? They just look at the frozen problem who has homogeneous reference estimates, approach them via comparison using the quantitative decay of the modulus of continuity of the coefficient, and then just extract regularity from the frozen problem using the homogeneous reference estimates. That's it. Okay? While here, the approach is direct. Because, of course, being non-uniformly elliptic, also the frozen problem, the a priori estimates are simply non-homogeneous, so in principle they cannot iterate. Okay, now let's have a look to what happens in the case of mu-elliptic problems. Well, the situation is pretty delicate there. Indeed, if we look at the contributions of Ladizhenskaya and Duraltseva, Giaquinta, Modica, and Suchek, we look at the book of Bildauer, the paper of Beck-Schmidt, there is always very heavy regularity assumptions imposed on coefficient, in general C2. I mean, a little bit far away from Schauder, right? Actually, as I was saying before, in these non-uniformly elliptic problems, if you plug in coefficient, the situation clarifies a lot. For instance, you can find them in these counterexamples are due to Giaquinta, Modica, and Suchek, and you can find them pretty much well explained in this book of Bildauer. What happens? If mu is larger than 3, then you can construct a non-autonomous area type integral, yes, with a C2 regular coefficient, which is 1 plus modulus of x squared, so nothing fancy, whose minimizer do not belong to W11. Cosa delta jumps. Moreover, if mu is equal 3, plane area case, in the plane area case, we can construct again a non-autonomous area type integral with an almost C2 coefficient whose minimizer do not belong to W11. So the situation concerning non-autonomous problems, regularity of coefficients, and mu ellipticity is pretty much delicate, pretty much difficult. So let's see what we can do under the point of view of Schauder theory. So what kind of a mu-elliptic problem we can handle, and how mu-ellipticity talks to Elder continuity, and in case also to anisotropy. Question, can we do it? Answer, let's try. Let's look at least to quite a reasonable class of mu-elliptic problems, which are those at nearly linear growth, so just think about the logarithmic energies. They are characterized by the fact that they are superlinear, right? So they, whenever divided by modulus of z, they just, and send z to plus infinity, you just blow up, but you blow up slower than any power larger than 1 of the gradient variable. And you can consider them as a sort of limiting case before classical linear growth conditions. Okay. Typical model is the LOGL energy, as I showed you. Now, if we want to quantify the non-uniformity of this object, we just look at the lowest eigenvalue of this action, the highest eigenvalue of this action, calculate the ellipticity ratio, and we see that it blows up very slow, but it blows up. And the same can be essentially said about iterated logarithms. Now, what can we do with these objects? In particular, what happens if we now plug in coefficients that are merely Elder continuous? Well, Schauder theory applies. What we have is that local minimizer to this object a locally Elder continuous gradient with precise identity between the Elder exponent of C and the Elder exponent of the gradient, of course, whenever beta stays between 0 and 1. We can say the same for the iterated logarithmic energy, but this time we lose half in the Elder continuity exponent for the gradient. Not a tragedy. we are moreover able to investigate the limiting configuration of the double phase energy as the ellipticity exponent approaches 1. The most reasonable example to look at is precisely the most reasonable model to look at is the following, where the elliptic part is given by an L log L energy and the Q phase is the usual one. Okay? Now, what happens with this guy? Well, I mean, L log L energies are limiting configurations in several fields. For instance, in harmonic analysis, there are limiting conditions for boundedness of maximal operators. And so what we want to do with this L log L double phase or the iterated logarithmic version. I mean, we can also treat more general cases than this, but okay, let's stick to the model for the sake of clarity. Well, in these cases, we immediately see that this double phase is non-uniformly elliptic, point by point. Therefore, all the theory developed for double phase problems simply breaks down in this situation. Any kind of perturbative approach simply fails. Trust me, I tried. You fail by any arbitrarily small delta. Okay, but using the right bunch of techniques, you can actually prove that local minimizer of the log double phase energy have locally elder continuous gradient, provided that Q is less than 1 plus alpha over n, and this is coherent with with the available literature, already with the case of double phase problems, right? The quantitatively superlinear one. And also to the case of multi-phase one, proven by Filomena and Mirko, where you have other elliptic phases with different powers. And we also offer a unified approach to several models at non-linear growth. And this is in a forthcoming paper with Filomena and Peter Asto. Okay, now, we already saw in the fundamental contribution of Bombieri, De Giorgi and Miranda, Ladizhanskaya and Duraltseva, Giaquinta, Modica and Sujic, that the combination of local boundedness plus a suitable high-dimensional non-uniformity constraint leads to sharp results. Yes? So, question mark, can we do this in our case? Well, yes, this is our first theorem formulated for the very basic model case of log double phase problems with a priori bounded minimizers. What we have is that whenever Q larger than 1 is strictly less than 1 plus alpha, then a priori bounded minimizers have their gradient, which is locally elder continuous in omega. But this is just a very special particular result of a more general theorem that embraces variational obstacle problems, okay? And again, I formulated this for the iterated logarithmic stuff, but you can be more general than that. Okay, so you have a priori bounded solutions to variational obstacle problems, where the obstacle satisfies just the classical assumptions you can see in the literature. What we can prove is that the gradient is locally elder continuous in omega. Moreover, if the model is non-singular, yes, if S is larger than 0, then if mu is equal 1, then the gradient is locally alpha elder continuous. While if mu is larger than 1, then there is the usual loss of alpha over 2. But yeah, it's nice that in the model case we recover the precise identity between the elder continuity exponent of the coefficient and the elder continuity exponent of the gradient. Of course, whenever alpha is strictly less than 1. Okay, can I make a few comments about how this business works? Well, one could say, okay, what is the very first problem with respect to the previous literature? Well, in the previous literature, there is heavy differentiation going on. As I said, you desperately need to use some form of, to pass to the second variation, meaning that you want to differentiate twice your problem. Once it's okay, is Euler-Lagrange equation. Second time means that you want to differentiate another time your differential operator. Problem, if your coefficient is Elder continuous, there is essentially nothing to differentiate. However, what does it mean, Elder continuity? Elder continuity means fractional differentiability for all s between 0 and alpha excluded, and all finite m. This means that your functional is almost 1 plus alpha times, is differentiable 1 plus alpha times. Okay? Almost. One say, okay, you developed a very nice fractional Moser iteration, so just, which goes along pretty nicely with bounded minimizers. So just push your Moser iteration and try to make it work with the obstacle problem. And this is an issue that pops out already in the uniformly elliptic case when p is less than 2 for subquadratic problems. You always, if you just look at the literature, you always have a loss in fractional differentiability of alpha over 2, always. How is this overcome when you deal with the usual double phase problems? You are using, in a crucial form, the pointwise uniform ellipticity of your integral. You are using results that are available only for uniformly elliptic problems. If you try to repeat the whole approaches, forgetting about the pointwise uniform ellipticity of your integrand, you'll simply get a non-uniformity threshold of the type q less than p plus alpha over 2. Or in our case, this would read q less than 1 plus alpha over 2. So something needs to be done in this respect. Well, what we do, we cook up a sort of hybrid reverse Elder inequality, meaning we control any arbitrarily high power of the gradient with the L1 energy, which is perfect, times an arbitrarily small power of the L infinity norm of the gradient. Okay, this comes by simply recovering that little bit of differentiability that allows you to embed your double difference, your Biesov spaces into Sobolev one. You're just grabbing that little bit. I mean, for whoever knows what I'm talking about. Okay. I mean, here I know that there are lots of experts in fractional problems. That's why I give this detail. Yes, so now one could say, okay, then perfect, you have a small power here, just put T2 plus infinity and then reabsorb. Problem, this is a linear iteration. You don't have, your integrability does increase so much to allow, to kill constants and essentially push your iteration till L infinity. So we need to couple this thing with the De Giorgi type iteration, fractional De Giorgi type iteration, okay? In which the latter information, which is the arbitrarily high control on the sides of the gradient, will be plugged as a final ingredient, if you want, okay? Okay, and this is just, let's say, some papers in which various forms of fractional differentiability has been successfully employed. Okay, now, also the obstacle situation might create some problems. Now, classically in the literature, there are two approaches to variational obstacle problems. First one is classical, is by now classical, is due to Duzar and Fuchs, and which is the linearization technique, right? What happens is that you can treat your constrained problem, your variational obstacle problem, you can turn it into a non-constrained problem with a non-homogeneity. And the non-homogeneity term behaves essentially as this quantity, okay? This simply happens using the characteristic function of the contact set. You can concentrate your problem, your non-homogeneity there, okay? Now, there are several works in this respect also involving non-uniformly elliptic operators, okay? because this technique is robust enough to support non-uniformity. However, this object makes sense whenever df is differentiable in the x variable. Otherwise, it simply breaks down. Therefore, in our case, it breaks down. Then there is the perturbative approach due to Coe. What do? You essentially compare your problem with a non-homogeneous one. You're essentially, again, using the same principle that you transform the presence of a convex constraint into a non-homogeneity for your problem. You go by comparison, you compare first to a non-homogeneous problem, and then to a homogeneous one. But the homogeneous one, to be of help in some sense, needs to be uniformly elliptic, needs to have homogeneous reference estimates, otherwise all the machinery breaks down. We are non-uniformly elliptic. Good. So also Coe's approach in our case breaks down. Okay, so what we do, we essentially observe that that fractional Moser iterations in a sense turns the constrained problem into something quite similar to this guy here, and still does the job. However, our results are new already for unconstrained problems. Okay, already the simple L-log-L model with a priori bounded minimizers is new. Okay, let's see if these results are sharp. Okay, this is what ChatGPT thinks that I have in mind when I talk about counterfractals. Whatever, was nice, I put it there. Okay, so let's see what happens when Q is larger than 1 plus alpha. Okay, so if this result is actually sharp or not. What we have here is, again, this is strongly inspired by the work of Balchi, Dilling, and Surnachov. Very nice results. And what we can prove, for instance, is the occurrence of Lavrentiev phenomenon. We can construct an Elder continuous coefficient, a smooth boundary datum, such as the infimum attained by the L-log-L energy over Dirichlet class with the smooth boundary datum U0 is strictly less than the infimum attained on the smaller subset defined upon C infinity with compact support maps. Okay? Moreover, we can also prove that the density of smooth maps with respect to modular convergence fails. So we essentially establish also the sharpness of the analogous of the paper of Bulijek, Gwiazda, and Shrechovsky for this class of problems. Okay, for L-log-L energies. But what I care more is about irregularity of minimizers. Okay, what happens is that whenever given any fixed epsilon, we can construct a modulating coefficient that is Elder continuous, a smooth boundary datum. I mean, Q is a cube, but of course can be taken also ball, such that solutions to this Dirichlet problem do not belong to W1P for all P larger than 1 plus epsilon. Okay? Now, why I like a lot this class of counterexamples? First of all, because they are scalar. In the uniformly elliptic setting, to spot irregularities, you need to go to the vectorial setting and play with anisotropy. Here is everything radial, everything scalar. In particular, these problems can be made non-singular, so it is infinity and whatever. Moreover, the domain is a cube, very innocuous. The boundary datum is smooth, so no singularity might arise from weird cusps on the boundary or for some misbehaving of the coefficient, of the boundary datum. The real responsible of all this mess is the misbehaving, is the coupling between coefficient and gradient variable. Let me just tell you how these things goes. This is the short tail of an honest boundary datum, a malicious competitor, and a cheating coefficient, which essentially flirts with both. Why? Well, because you can essentially construct a competitor that is very regular, okay, by simply considering modifications of the characteristic functions on cones whose tips are on the fractal, that, as you can see, lies in Rn-1. So you're taking these cones like this. Now, playing with the amplitude of the cone, you can in some sense construct coefficient and competitor that are made in such a way that the gradient is non-zero whenever A is 0. What happens here? The fact that coefficient is allowed to vanish is essentially killing the singularities or hiding the singularities of your competitor. In particular, the Q part is annihilated, meaning that you have a very artificially low energy. Moreover, how do you construct the honest boundary datum? You say you just cut off the fractal. Outside everything is smooth. Therefore, you obtain the malicious competitor and the honest boundary datum that have the same traces on the boundary. Therefore, U star is admissible. And this provokes this essentially forces minimizer to have a very low energy. Therefore, by prescribing very high traces at the bottom and at the top of the cube, what happens? You simply do not have enough energy to go from minus 100,000 to plus 100,000, and therefore you're forced to, in some sense, break somewhere. And therefore singularity develop precisely on the fractal. In this way, you are forcing your set of non-Lebesgue points to contain a piece of the fractal. This means that the Hausdorff dimension of the set of essential discontinuity points of your minimizer is larger or equal than n minus 1 minus epsilon, meaning that your minimizer cannot belong to W1P plus epsilon for all epsilon. Now, this counterexample essentially doesn't forbid the possibility of realizing L-log-L estimates, okay? But since we were interested into pointwise regularity, for sure you are not reaching W1Q or W1 infinity, okay? Now, this proof, as I said, builds on this very nice work of Balci-Ding and Surnachev. In particular, they assume both delta 2 and nabla 2, but since double phase energy is a splitting structure, you can just forget about the nabla 2. Now, in particular, we can also extend these counterexamples to the more general area type functionals. Okay? Here, singularities emerge whenever Q is larger than 1 plus alpha. This is mu elliptic. Mu is P plus 1, where P and Q are larger than 1, and that's it. I don't have regularity for this guy. I only have irregularity. However, whenever one works with these non-uniformly elliptic problems, what is a little bit evident is that the real interaction that is built up is not between Q and 1, as it comes from essentially from a comparison of capacities, which is what happens in these counterexamples. The real interaction that in the case of pointwise uniform ellipticity is simply hidden, if you like, what happens is that Q must talk to 2 minus mu, not to 1. So, if we just believe that this should be the right condition granting regularity, right? Because, I mean, for PQ non-uniformity, condition for a condition for kinging out for granting integrability up to an exponent, for instance, is Q less than P plus alpha. Okay, so this is pretty much coherent. However, if we just recall that mu is P plus 1, we obtain these quite scaring conditions that tells you that if you want to have some hope of regularity, okay, you must for sure force Q to stay below 1 plus alpha. And 2 minus mu is less than 1 plus alpha, being mu larger than 1. Moreover, this condition might be satisfied. So if you want to take mu quantitatively away from 1, right, such a way that this condition makes sense, you are in some sense forced to take alpha quite high. I mean, you cannot take any arbitrarily low amount of Elder continuity in your coefficients. So this points in the direction that these log double phase problems might be the limiting configurations in which Q anisotropy, mu ellipticity, and Elder continuous coefficient with arbitrary exponent, okay, can coexist and still have hopes of regularity. Okay, and of course, these counterexamples are perfectly coherent with the achievement of Giaquinta, Modica, and Suchek. Okay? Okay, now those are the two papers from which this talk is taken, and I thank you very much for the attention.